Would this the setup be damaged by vibration or shock? Because I can see how you can apply this for a building or for a small community, maybe even cityscapes eventually, and perhaps even space travel, because you don't shake very much in space. But for vehicle applications, you have to be worried about vibration, shock, sudden changes in direction. Would that?
Well, I mean, this device, as it is now, is not small enough to fit in a car. It's small enough to fit in a truck. And one of the applications we did apply to money, to the government for money for, was to put this in a truck and use it as a source of X-ray radiation for inspection of roads and bridges. The device that is operating in Middlesex, I wouldn't put that in a truck. It's quite delicate.
Some days you want to put it in a truck and just bye.
Right.
Next one.
By the way, the device is called Focus Fusion 1. And on days that it's operating well, we call it FOFU. On days that it's not operating well, it's that damn machine. So with reasonable engineering design, in other words, putting in shock absorbers and so on, yeah, we think it could be carried in a truck. Whether it could be carried in an all-terrain vehicle, I don't know if you're looking for other things. But certainly a truck, a ship, things like that. This, with reasonable engineering, it could certainly do.
An aircraft, maybe?
Yeah, probably an aircraft. Obviously, you would have a concern of, with an aircraft, of impact. Then you're subjecting something to extremely high stresses. And you do have short-lived, and I'm talking about very short-lived, these are radioactive elements with half-lives of 20 minutes. You have, potential for release of short-lived radioactivity. It would have to be thought about for aircraft. But if you have unlimited supplies of electricity, there are a lot of alternatives. I always loved the idea that actually Rand Corporation, of all people, studied back in the 70s, which was evacuated magnetic levitation trains. If you put a magnetic levitation train in an evacuated tube, you essentially have no resistance. And you can send it up to nearly orbital speeds. So they had a plan where you could dig a tunnel from New York to LA or San Francisco, get across the country in 30 minutes. And you actually would be using almost no energy because you'd get the energy back as you slowed down. So there are ways to get around using as many planes as we have in the air right now.
So you guys are looking for what, $20 to $30 million to do this engineering program that you're talking, the prototype, or are you looking for $20, $30 million to do what?
Well, as I say, right now we're trying to complete a $900,000 offering to continue the scientific experiment. Mm-hmm. And we're going to need another offering of approximately, probably of the order of $1.5 million, just to continue and to complete this experiment. The 20 to 30 million is our estimate of what it would take to do the engineering work to produce a prototype. The engineering work, is basically solving three problems. One is, how do you get the waste heat out of this very small device? You're going to have to be taking out several megawatts of waste heat. That's possible, but it's certainly on the cutting edge of cooling technology. Second of all, you need very high efficiency in your ion beam converter, roughly 80%, and you need very high efficiency in this X-ray converter, which is a new device, although it's based on extremely well accepted photoelectric principles. So those three projects, you're going to need maybe a staff of 100 working on that. That's our current estimate.
With that excess heat, could that be used to generate electricity old-fashioned way? Heating water and turning turbines?
The problem with doing it that way is that, well, first of all, you're giving up your enormous cost advantage. If you take, for example, a natural gas-fired generator, 80% of the capital cost is after you've produced the energy. So even if you were using, 0-point energy, produce the energy for free, you wouldn't be able to reduce your capital cost by more than 20%. This device, we estimate, could be mass-produced for something of the order of 300 grand. So that would be a tenfold reduction in the capital cost. So that's one reason why you don't...
300 grand to produce a 5 megawatt
Right.
producer, and what was the factor?
That's, we're talking about something like 6 cents per kilowatt
Yeah, so
installed
you're saying
as
300
opposed to $1 per kilowatt installed today.
Right.
So you'd be giving up that advantage. The other problem is your efficiency of energy conversion goes way down, and that might make it impossible to get net energy. We're talking about if we have an 80% efficiency of energy conversion, when you take into account all the energy losses, other losses in the system, then you end up with about a 40 or 50% overall thermodynamic efficiency. So if you were using a heat cycle, which would probably be itself 40 or 50% efficient, then you might get down to almost a 0% overall efficiency. So you really need high efficiency in getting this energy out.
And 5 megawatts powers
About
1,000 homes?
1,000 homes.
a few thousand, I think.
2,000 homes, okay.
It depends on whether you're talking about electricity use or total energy use. If it's total energy use, then, it's more like 1,000 homes. If it was electricity, it would be something like 5,000 homes.
How long do you expect one of these to last in operation?
Well, the part that's going to get the most wear and tear is this electrode. That's going to be eroded because it's going to be exposed to high heat. And even though we're cooling it, there's going to be an outer layer. So we hope that these electrodes will last about a month, and then there'd be a maintenance cycle to shut them down for several hours, replace them. Of course, the material will just be recycled. The whole generator, hopefully it will last, 20, 30 years. Really, there's no, its parts are all replaceable. There's no reason why you couldn't continuously replace it, and the machine itself would last pretty much indefinitely.
So you think a 5 megawatt machine is a machine that you could go to commercial market with, or you'd have to scale it up further?
No, I think it has great advantages. If you have a basic unit that's 5 megawatt, you can plop it right next to the load. Once we convince people that these are safe devices, we would be putting these in electrical substations and delivering power basically at a neighborhood level.
Yeah.
Now that has a great advantage in security. It basically means that if you get blacked out, you're only blacking out the neighborhood, you're not blacking out the northeast. And if most of you'd maintain the grid, but if most of your energy is being shipped over very short distances, you also save enormously on energy losses. And if you're looking to the developing world, where most of the energy market will eventually be, it's a great advantage to have very low infrastructure costs initially. You go to places that have no infrastructure whatsoever, you plop one of these generators down and you say, okay, we're supplying energy to a township. And then all you're doing is you're creating distribution infrastructure, which is a hell of a lot cheaper than a transmission structure.
All right, well, one more question?
Yes, you mentioned about the waste heat involved, despite the fact the plasma focus is so small. Will that be a problem if you try and scale up one of these?
No, I mean, we're expecting thermodynamic efficiency, which is in the same general ballpark as what we have now, which is about 40–50%, which means that for every unit of power, you're going to have a unit of waste heat. If you have a 5 megawatt isolated generator, the waste heat is easier to deal with. You can probably, almost certainly at that level, vent it directly to the atmosphere. You don't need water cooling, which creates problems. If you have an application, such as an aluminum factory, where you have to plop these things down and have 20 units working together, then you're probably going to have your conventional cooling. You're going to have a source of water supply, cooling tower, and so on. But again, dispersion is very good. If you can avoid using the water supply for cooling, you have a lot of environmental gains. First of all, you don't have to worry about the fish getting caught up in the intake. You don't have to worry about the fish being killed by the warm water that you're putting back in the system. You don't have to worry about running out of water if you've got a relatively dry area. So again, having an inherently small unit be your most efficient unit is a big advantage. And these would be small enough, as I say, for mass production.
It would be a problem though in a vacuum, wouldn't it? If you use it on a spacecraft.
Yeah, the space is a real it's a real difficult problem because the only way of getting rid of energy is radiating it. So you'd have to have a big radiator. There are ideas. I don't know whether it was Derek. Were you the one who told me about the curtain of particles? Somebody.
Somebody did.
All right, not Derek.
All right, another space
There's
cadet.
one idea of having a curtain of fluid that's in particle form, so droplets. And these droplets will have enormous surface area. So you have this curtain going down the side of the spacecraft, and then you have collectors at the bottom. Of course, you can do this in space because you can control where these particles are going. So in theory, you can get very high efficiencies of energy radiation. But for space travel, that would be the key problem, is keeping the mass of the radiator relatively low.
Or you could use helium. Helium has a very high specific heat, I think second highest compared to hydrogen. And you could use helium from this reactor, so if you can somehow use the helium
Right.
heat sink.
Yeah, well, as I say, it's mainly a question that when you radiate something, the maximum you can radiate is defined by the black body law. And unless you can get it up to very high temperatures, you need a lot of surface area.
Well, first things first.
Actually, wait, one more comment. I don't want to
Yeah.
leave without this. The Iter thing, I know in a way it seems like we're trash talking Iter, but I want to make it clear that the bargain they faced was kind of not getting funded. I mean, it's a very tricky situation, and to me, it appears to be more of a marketing issue. That the fusion community wasn't able to market themselves well to the public or to Congress, and we need to work with them. I mean, they do a lot of amazing science. They're actually pushing a lot of envelopes with their Iter research, a lot of basic stuff that feeds the whole community, so I don't want to...
Well, the key thing is the fusion effort obviously needs more diversity. It needs more funding. Most of the projects that we're talking about, our project, the other people working on PB11, our funding needs are very modest. I mean, the Board of Public Utilities in New Jersey has a subsidy program to reduce the cost of energy for consumers, which is, I think, something of the order of $120 million per year. So that's the state of New Jersey. So the state of New Jersey could take 7% of that subsidy and fund this $20 or $30 million project for 3 years. I mean, the amounts of money we're talking about are very small. A colleague of mine is getting funding, who's Italian, although he's living in Canada, he's getting funding from a town, from one of the Italian cities, municipal funds. So this amount of money, this research is pocket change to almost any governmental entity.
Did you talk about Rush Holt?
It's really a scandal.
We're talking about pocket change to Angelina Jolie. I mean, I don't get, why can't you talk to Brad Pitt or George Clooney? Half a movie would fund you guys.
There you go.
I don't get it.
Okay, let's go talk to
Well,
George.
we're going to work on it, and we'll talk more about which celebrities to hit up. If anybody knows George Clooney, well, we want the info. And
He's a current contract.
exactly.
I mean,
So first things first, we'll keep working on our feasibility. We wish the best of luck to all the fusion efforts, including Iter. And thanks everybody so much for coming. And happy solstice. And we'll definitely have questions. I'll just end the formal period, so we'll end our online stream. Thank you, Eric, for all you've done.